So in this video lecture, we are going to talk about wideband frequency modulation, which is abbreviated as WBFM for short. And we already know the condition for wideband frequency modulation is this, that is magnitude of KF into AT has to be very greater than 1. If it is not the case, then we know that the case is NBFM, that is narrowband frequency modulation, and we have already done an analysis about narrowband frequency modulation in the previous video. And what is AT? AT is nothing but it is integral of your message signal MT, right? So now to be able to understand how wideband frequency modulated signals spectrum is plotted and how the analysis about its bandwidth calculation is done, let us take an example of this as our message signal. The black signal that you see here is the message signal, and we have taken it a staircase approximation of that, right? Staircase approximation, we have taken this on some reason. So let us have a look at this first. If this happens to be the plot of our frequency modulated signal, then for frequency modulated signal we already know that if the frequency will be high wherever the amplitude or wherever the value of this signal is high, and the frequency will be low wherever we have got these low values of amplitude. Now in this case, since we have taken the staircase approximation of our signal, so we are assuming that over that particular interval the signal will not change. So the staircase approximation is such that in each cell, let's call these rectangles as cells, in each cell the amplitude remains constant irrespective of this shape of signal which changes. And if we take the size of these rectangle, that is the width of these rectangles, which is very small, then this staircase approximation will be able to replicate this exact signal. So that's what we are doing here. And had it been this had this diagram been the diagram of frequency modulated wave, we can already see that for this particular staircase approximation, since the value of amplitude is high here, so you will have a high frequency signal here. That means you will have in addition to carrier frequency, there will be additional frequency, as we know from the equation of your frequency modulation. So this is high here, and since here the amplitude is low as compared to this one, so we will have a relatively low frequency here as compared to the carrier frequency. And this can be seen by this particular equation. The instantaneous frequency is the actual carrier frequency plus kf into mtk. What is this mtk? Let us consider this kth time tk, and this is the beginning of kth cell, and whatever is the amplitude here is represented by mtk. So if this mtk can be positive or negative, or it can have high or low value depending upon your signal, and that is how your instantaneous frequency in the frequency modulated signal will vary. Now how do we select this width? We should take the width of this according to the sampling theorem. Again, we know that if we want to reconstruct this analog signal from this discrete version, from this staircase approximation, then we have to use sampling theorem. And as per sampling theorem, if we know that message signal is band limited to B hertz and minimum and maximum amplitudes are minus MP and MP, then in that case the samples should be taken at with the maximum distance between the consecutive samples as 1 over 2b. This is what we know from the sampling theorem already. So the width has to be at max 1 over 2b. You can take any width which is smaller than this or even equal to this. So in this condition we have made this. Now the frequency modulated signal will be plotted for all of the cells. I have only shown for 2 cells here. You have to plot it for all of the cells, right? So now what is the idea? We want to plot the frequency domain diagram here. These both are time domain representations. This is for message signal and this is for the frequency modulated signal, and I have shown it for only 2 cells here, right? Now the idea is to generate this frequency domain plot. So how do we generate the frequency domain plot? So let us talk about this staircase approximation for which this frequency modulated signal is already drawn here. If you see at this particular cell, this sinusoidal signal which has high frequency here, and if you try to plot its spectrum, it will be definitely a sinc function. Why it will be a sinc function? Why it will not be a spike function? We already know this from our discussion on amplitude modulated signals and waves, where we had a rect function, and if we take the spectrum of rect function, it will be sync function, and that sync will be centered around origin. But if we multiply a sinusoidal signal to that particular rect function, then as per the modulation theorem, that rect will be shifted to an appropriate frequency, the instantaneous frequency that you see here. So the spectrum for this particular cell will be a sync function which is shifted to an appropriate instantaneous frequency. So might be for this particular slot the spectrum is this rect function, and similarly for this particular slot the spectrum might be here. So we have to plot it for all possible cells here, and that's how we will get these sync pulses, and their corresponding amplitudes will vary accordingly. So now imagine a case when we shrink the width of these cells to zero. We will get the exact frequency modulated wave here in time domain, and the corresponding frequency domain plot can be obtained. Now it is important to know that if the sync would have been infinite in extent, the spectrum of this cell would have been a spike only. But since this sync is truncated to few values, this is a sine function which is multiplied by a rect function, so the spectrum has become sync.